Hello and welcome to the Daily Space for today, Tuesday, June 23rd, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today's news seems to be designed by blathers of Animal Crossing. We get one of everything, but only one. And no more. For instance, let's consider Pluto. We got one and only one flyby of one and only one large Kuiper Belt object. This means when we try to understand new ideas about this distant world, we can only look around the data we already have in new ways and hope to find what we need. This kind of let's look through the data in a fresh way foraging can turn up awesome results, however. For instance, researchers at the University of California, Santa Cruz wanted to understand how Pluto formed and managed to maintain a subsurface liquid ocean despite being at the edge of the solar system. So they did some theory work and then went looking through the New Horizons data to find out what the data said was possible. There were two schools of thought prior to today's story. The first group said Pluto started out cold and by some unknown process, its internal ice melted. The other group said Pluto had a hot start and started with oceans that later freezed out. Conveniently, these two theories produce a Pluto that looks slightly different. The hot start theory requires evidence of expansion features on the surface that would form as ice expands while freezing. An event that melts the oceans later would likely be associated with compression features instead. Seeking to put an end to the where did the oceans come from debate, this team poured through the data and found clear evidence of a hot past. As first author and University of California, Santa Cruz graduate student Carver Bierson explained, we see lots of evidence of expansion, but we don't see any evidence of compression. So the observations are more consistent with Pluto starting with a liquid ocean. Of course, these observations lead to a second question. Where did Pluto get the energy for a hot start? The two main sources of planetary heat are radioactive decay and gravitational energy from planetary formation. It's unlikely that radioactive materials could generate as much energy as is needed, but really fast formation could do the trick. Co-author Francis Nimno explains that if the gravitational energy builds up fast enough, the heat gets trapped inside. To contain enough heat to keep a liquid ocean, Pluto would have had to have formed in under 30,000 years. Any slower, and heat would have had time to radiate away to surrounding space instead of getting trapped inside Pluto. These findings could mean that large KBOs such as Eris and Makemake could also have similar icy oceans if they formed in a similar fashion. Clearly, one flyby of one large KBO is not enough, and we are really hoping to someday get more data. One of the running jokes in astronomy has been that 1 object is a paper on a new phenomena, 2 to 5 is the start of a new field of investigation, and at 6 examples, you get to start doing statistics. This has finally started to change with large-scale surveys of the sky, but there is still a problem with there being so many things out there that we only have a handful of examples for some things, and it's easy to rediscover things by accident. And the time and energy that goes into that whole "we have discovered" process prior to realizing you actually haven't discovered something, well, it's a lot. To try to make it easier to know what's already out there, folks have been making and sharing catalogs for hundreds of years. Charles Messieurs' catalog of bright extended objects was originally intended to help people know when they had found an actual comet and when they had just rediscovered a globular cluster for the nth time. Today, this Let's Make a Catalog tradition is carried forward by the Breakthrough Listen project, which is taking more of a guidebook approach to listing out what can be found among the stars. They list out more than 700 distinct radio targets, with the goal of describing one of every kind of naturally occurring radio signal. Like a nature guide, it doesn't just list what prototypes for each class of object should look like, it also lists out the extremes that can be seen. There are also objects that are anomalies, and here I'm going to quote what anomaly means directly from the press release. Anomalies are enigmatic targets whose behavior is currently not satisfactorily explained. For instance, the famous Tabby star with its bizarre dimming behavior, Oumuamua, the interstellar object that passed near Earth in 2017, unexplained optical pulses that last mere nanoseconds, and stars with excess infrared radiation that could conceivably be explained as waste heat from alien megastructures. Yes, folks, I said alien megastructures. Now, they aren't trying to say there are aliens. They are trying to say there could be aliens and to make it as easy as possible to identify them against the background noise of our universe. Just as the Messieurs catalog made it easier to discern the real comets against the background of clusters, nebulae, and galaxies that litter the sky, it is hoped that the Breakthrough Listen Project's catalog will make it easier to identify possible signals of extraterrestrial life against the background of pulsars, quasars, and young stars that all emit their own radio signals naturally. The catalog also discusses what different technosignatures of advanced civilizations could look like. This catalog also contains control samples that shouldn't produce signals and can be used to calibrate instruments, as well as discussion on how to classify both the included objects and future new kinds of radio sources. While the author's goal is to make finding life easier, this catalog will benefit the entire astronomy field. As put by lead author Brian Lackey, the catalog is not just limited to SETI, though. My hope is that any program with a new capability may use the Exotica catalog as a shakedown cruise around the universe. Ultimately, to understand our universe, we want to find more than one of everything. Heck, we really want to find more than 6 or even 600. We want complete populations of objects so that we can understand every facet of an object in every possible combination of circumstances. But sometimes just finding one is hard enough. We've known since the 1990s that hot Jupiters, massive Jupiter-like worlds can exist snuggled up to their host stars. What we haven't known is how they get there. It could be they formed there or migrated there, or at some point in their solar system's history, it could even be all of the above. To understand these systems, we need examples of young stars with young planets so we can see what is possible. And finally, we have one example. HIP 67522b is a hot Jupiter found in TESS data that is orbiting its star every 7 days. That star, it's only 17 million years old, and that makes this a young planet. While we still can't know if the world formed there or migrated there early in the star system's history, this singular example does tell us that not all hot Jupiters migrate there 1 billion or more years after a solar system's evolution. It's a start. One object can be the start of an awful lot of science. But here's to hoping they find many more examples quickly. But for now, that's all the science we have for today. I'm now going to hang around and answer the questions live for those watching here on twitch.tv. But before I do that, I just want to say thanks for watching. This has been The Daily Space.